Greetings and salutations and welcome back. In this topic we will be studying momentum in two dimensions. Importantly, it is the application of a force which will produce a change in velocity or a change in momentum of an object. If we know the initial and final velocity, we can calculate the change in velocity and then use this information to calculate the average acceleration. We can then use Newton's third law to calculate the average force applied to the surface by the particle. We can derive the equation force is equal to the change in momentum over time. And by calculating the change in momentum, we can calculate the force applied to a surface. This question requires us to calculate the change in momentum of a ball using a vector diagram. We are told that the ball is travelling at the same speed before and after it bounces. The first step is to write the equation for the change of momentum, which will be the final momentum minus the initial momentum. When drawing the vector diagram, it is important to include the labels for the vectors and the direction on the vectors. Notice that the resultant change in momentum vector is at 90 degrees to the surface. Since both the final momentum vector and the initial momentum vector have the same length, and the internal angles are 60 degrees, we can see that the change in momentum vector will in fact make an equilateral triangle, as all of the angles will be 60 degrees. This means that it will have the same length as the other two vectors. Therefore, the magnitude of the vector will be 4.54 kilograms meters second to the minus 1, but importantly it will be at 90 degrees to the wall. We're now going to use the conservation of momentum law to solve a range of problems. Firstly, the law of conservation of momentum states that the total momentum before and after an event is conserved. Our first type of problem is an airtable collision. We are going to compare the magnitude and directions of the total momentum vectors before and after the event. The second type of problem involves an explosion. We will use the conservation of momentum to describe the motion of the fragments after the explosion. Finally, we will use conservation of momentum to describe the motion of spacecraft. In our first example, we will look at the emission of discrete particles. Finally, we will look at how the reflection of light particles or photons can be used to accelerate a solar sail, and then compare that acceleration to one produced where the photons are absorbed. This question looks at using photons of light from the sun to accelerate a spacecraft. Now it turns out that photons in fact have momentum. This question wants us to use the change in momentum of the photons. To do this, we need to draw vector diagrams to show that there is a greater change in momentum of the photons when they are reflected rather than absorbed by the solar sail. And we're only going to consider photons that are at 90 degrees to the sail. To begin with, I'm going to look at the example where the photons are being reflected by the sail. I've drawn two vectors here for the initial momentum of the photons and the final momentums of the photons. Notice that they have a change in direction, and to help emphasize this I've used a different color as well. Mathematically, the change in momentum is going to be the final momentum minus the initial momentum. As a vector diagram, the change in momentum, which I've drawn here in black, is equal to the sum of the two individual momenta. Now for the example where the photon is being absorbed, I still have the initial momentum coming in as blue, but the total momentum is going to be equal to 0. Therefore, mathematically, the change in momentum is going to be equal to the minus of the initial momentum. So now if we do a vector diagram, the change in momentum is simply going to be equal to the magnitude of the initial momentum. So you can see from the vector diagrams that the change in momentum for the photons that are reflected is going to be much greater than the photon that is being absorbed by the sail. And the reflected photon for the absorbed sail has no momentum. For part B, we're asked to explain why a solar sail that reflects photons will undergo a greater acceleration than a solar sail that absorbs photons. The key to this question is to now explain the greater acceleration that is experienced by the solar sail. We can use the relationship that force is equal to the change of momentum over time to explain that the reflected photons have a greater change of momentum in the same amount of time than the absorbed photons, and hence the sail will experience a greater force in that time interval. And using Newton's third law, and that force is equal to ma, the acceleration acting on the sail is going to be greater.